Chemistry in action. Chemistry plays a very important role in our everyday life. Many substances used in our daily life are chemical compounds like sugar, soap, synthetic clothes, dyes, medicines, detergents, insecticides, fertilizer, cosmetics, perfumes, your toothbrush, toothpaste, etc. And there is in fact no aspect of our life which is not affected by the developments in chemistry. In this chapter we will be learning the chemicals involved in 5 different topics. The topics covered are dyes, drugs, soaps, detergents and explosives. First we will see about dyes. Dyes are colored compounds having the property of imparting their color to other substances like textile fiber, paper, foodstuffs, etc. All dyes should be colored, but all colored compounds need not be functioning as dyes. So for colored compounds to be a dye, there are certain requirements to be satisfied. So requirements are: it must have a suitable color, it should be capable of fixing itself on the material to be dyed, it must be fast. The meaning is that it must be able to resist the action of light, water, acid and alkalis, particularly the latter because clothes are cleaned using dilute acids or alkalis and detergents. And dyes must also be fast, that is they should resist various organic solvents used in dry cleaning, and should be preferably soluble in water or aqueous solutions because in such cases it is easier for application of the dyes on the material. Now we will see the chemical nature of dyes. So framework of most dyes, they are aromatic ring like benzene, naphthalene, etc. And occasionally there are heterocyclic nuclei also. So you know the structure of benzene. This is benzene. Naphthalene is 2 fused benzene rings. And heterocyclic nuclei are also there. Heterocyclic means there is an element other than carbon. So in this, instead of this carbon, if you have a nitrogen or oxygen, it becomes a heterocyclic compound. And there are substituents on the ring which can be polar groups like OH, hydroxy, amino NH2, or nitro NO2, or carboxyl which is COOH, and sulfonic groups which is SO3H. And the groups can be identified as chromophores and oxochromes. So chromophores are the groups which are responsible for color, like the groups with double bond. Suppose in some dyes there are N double bond N, and there are dyes where you have benzene ring, and in all these you can see that there are double bonds which are responsible for the color. And oxochromes are the groups which enhance the color. So groups like OH, SO3H and NH2, when present along with the chromophores, it intensifies the color. And the fixing properties of dyes are due to the acidic or basic oxochrome groups. So here OH and SO3H are acidic groups and NH2 is a basic group. So the dyes are getting fixed to the fabric due to the oxochrome groups which are acidic or basic. Now polar oxochrome groups makes the dye water soluble and bind to the dye fabric by interaction with oppositely charged groups of the fabric. So if the dye has positively charged polar groups, then it will interact with a negatively charged group in the fabric. Now we will come to the nomenclature. So chemical names of dyes are generally very complicated. If you see the IUPAC name, they are complicated. So therefore trade names are used for indicating dyes. So alphabetic letters are used to indicate the shade of the dye. For example, B for blue, O for orange, R for red, G for yellow. The letters can be repeated to show the greater intensity of the color. And some letters are used to refer some specific properties. If we include F, it refers fast to light. So WF is fast to washing. D is direct dyes. S is acid dyes. Now, Society of Dyers and Colorists have a list of name and colors of various dyes, which is known as the color index. And in this, each dye has been assigned its individual color number or color index number. We'll come to classification of dyes. So dyes can be broadly classified into two ways. One is classification based on structure, which is called the chemical classification. Another one is classification based on the method of application. The first one is the classification based on structure, that is chemical classification. So in this system, the dyes are classified based on the structure and the type of chromophore present in them. And according to this can be classified into the following: nitro and nitroso dyes, azo dyes, diphenyl methane dyes, triphenyl methane dye, anthraquinone dye, indigoid dye, phthalene and xanthine dyes, heterocyclic dyes, and phthalocyanine dyes. So the first one is nitro and nitroso dyes. So in this class, the chromophores are NO2 or NO2 or NO groups. So they are generally polynitro derivatives of phenols. So phenol is OH group attached to benzene. So these contain NO2 groups as chromophore and hydroxyl groups as oxochromes. So some examples are picric acid. So you can see that in picric acid there are 3 NO2 groups attached to the benzene ring, and these are the chromophores, and OH is the oxochrome. Similarly, this is Martase yellow, this is naphthol yellow, and this is gambine R. The second one is the azo dye. These contain one or more azo group. Azo groups are N double bond N groups, and these are the primary chromophores. And along the chromophore, there is oxochromes, which are usually NH2, NR2, OH, SO3H, etc. An example is methyl orange. You know very well what is methyl orange. It is an indicator used in acid-base titration. Another example is para red, and there are other examples like Congo red. In all these, you can see the presence of this N double bond N present here, which is the chromophore. And along with the chromophore in methyl orange, you can see the presence of other groups like SO3H and NR2, which is NCS3-2. These are the oxochromes. And in para red, the oxochrome is the OH group. Diphenyl methane dyes. These have a basic diphenyl methane skeleton. Diphenylmethane skeleton refers to when a carbon is attached to two benzene rings. This is a diphenylmethane skeleton. Here one of the aromatic ring is in the quinonoid form, which is the chromophore. Oxochromes are NH2, NR2, etc. So these are examples of diphenylmethane dyes. Quinonoid form is quinone-like structure. The structure of quinone is this. This is quinone. So when we say that the benzene ring is in the quinonoid form, the form is similar to that of structure of quinone and it is existing in this form. So this is the quinonoid form. So you can see here in this dye, this structure is in the quinonoid form and this is the chromophore. And oxochrome is NCH3 twice. This is auramine O. Auramine G also, the carbon is attached to two benzene rings and one of them is in the quinonoid form. And the oxochrome is NHCH3. Triphenylmethane dyes. Now we saw diphenylmethane dyes in which the central carbon is attached to two aromatic rings, one of which is in the quinonoid form. In triphenylmethane dyes, the central carbon atom is bonded to three aromatic rings, one of which is in the quinonoid form, which is acting as the chromophore. Oxochromes are NH2, NR2, OH, etc. Now, when the oxochromes are introduced in the phenyl rings, the resultant colorless compounds are known as the leucocompounds. These leucocompounds on oxidation are converted to colorless color bases, which in presence of acids form a colored dye. So this is an example of triphenylmethane dye. This is malachite green. You can see that here the central carbon is attached to three aromatic rings, one of which is in the quinonoid form. And this is what is the chromophore. And we have oxochromes which are NR2 or NCH3 twice attached to it. This malachite green is green in color. Other examples are rosanilin and crystal violet. You can see that the structure in all the three are same. The central carbon atom attached to three aromatic rings, out of which one is in the quinonoid form. Anthraquinone dyes. These are derivatives of anthraquinone. Anthraquinone has a structure like this. And the paraquinoid is the chromophore. So the paraquinoid, this part is the chromophore. An example is alizarin. And this is the structure of alizarin. You can see that it is a derivative of anthraquinone. And this is the color of alizarin. Next is indigoid dye. The chromophore in these dyes are the carbonyl groups. This is the structure of an indigo, which is an example of indigoid dye. And here these carbonyl groups are the Chromophore. Indigo is the oldest known organic dye. And this is the color of indigo, you know very well, the color of your blue jeans. Now next is phthalene and xanthine dyes. These are formed by condensation of phenols with phthalic anhydride in the presence of a dehydrating agent like concentrated sulfuric acid. Example of phthalene dye is phenolphthalein. You know very well what is phenolphthalein. It is an indicator used in acid-base titrations. Example of xanthine dye is fluorescein, eosin, uranin. Next is heterocyclic dyes. These contain at least one heterocyclic ring in the molecule. So there will be a atom other than carbon in the ring. For example, if you have a ring like this, which is now this is benzene, and instead of this carbon, if you have nitrogen, oxygen or sulfur or any other element other than carbon, this becomes a heterocyclic ring. Example of dyes of these type are acryflavine, cyanine, methylene blue, etc. Next is phthalocyanine dyes. Phthalocyanines are a class of organic dyes and pigments. These are metal complexes of a metal with a ligand which resembles porphyrin ring of heme or chlorophyll. So heme or chlorophyll contains a ring which is called the porphyrin ring, which looks like this. This is the porphyrin ring. And in heme, these nitrogens are coordinated to iron. In chlorophyll, the nitrogens are coordinated to magnesium. So you can see the structure of heme, which contains this porphyrin ring as the ligand. So this is the structure of heme, which contains the porphyrin ring. Now, phthalocyanine contains a ligand which is similar to this porphyrin, and it contains 4 nitrogen atoms instead of the 4 methylidene groups. So instead of these atoms here, there are 4 nitrogen atoms. So this is how phthalocyanine looks like. And an example of dye which is coming in phthalocyanine dyes is monastrel fast blue. This is a copper complex of phthalocyanine. The next classification is based on application. The method of application of a dye to a material depends on the nature of both the dye and the material. The material or the fiber, it can be polar or moderately polar or weakly polar. The dyes, to color them, should also have similar polarity. The dyes must be fast too. To achieve this, some special techniques are employed, and dyes are often classified on the basis of this. They are classified as direct or substantive dyes, modern dyes, wet dyes, ingrain dyes or azoid dyes, also called developed dyes, and disperse dyes. The first one is direct or substantive dyes. These dyes are polar dyes and are used for polar fabrics like wool or moderately polar fabrics like cotton, rayon, etc. These dyes are applied to the fabric by direct immersion in an aqueous solution of the dye, then taking it out and then removing the excess of solution and drying. So it is the simplest process. These are further subdivided into acid dyes and basic dyes. So acid dyes, these dyes contain acidic oxochromes. So it can have OH group or SO3H sulfonic acid groups as oxochromes. So examples are nitronaphthols, which is marked as yellow, and sodium salts of sulfonic acids. These dye wool and silk due to interaction of the polar acidic group of the dye with the basic group, which is the NH2 group of the fabric. So the fabric has the NH2 group and the dye has the OH group. So this is the basic group and this is the acidic group. And the interaction of these two leads to the binding of the dye on the fiber. In basic dyes, the oxochromes are basic in nature. These are salts of color bases with hydrochloric acid or zinc chloride. These can dye animal fibers directly. Example is malachite green. Second type of dye is mordant dye. So dyes which have no natural affinity for fabric cannot be applied directly, as we saw in the direct dyes. So these are applied with the help of other agents called mordants. Such dyes are called mordant dyes. So what are mordants? A mordant or dye fixative is a substance used to set or bind dyes on the fabric by forming a coordination with the dye, which then attaches to the fabric or the tissue. Salts of iron and chromium and acidic substances like tannic acid, etc., may be used as mordant. So here you can see this is the mordant and it has a site for binding with the tissue. And it has also a site for binding with the dye. So that is how the dye is held on the fabric. That is how through the mordant the dye is held on the fabric. Acid dyes require basic mordant and basic dyes require acidic mordant. So here a fabric is first treated with a mordant and then with the dye. The mordant first combines with the acidic or basic group, whatever is present on the fabric, and then it combines with the acidic or basic group of the dye. Example of a mordant dye is alizarin. And mordant used for alizarin is aluminum hydroxide. So the aluminum hydroxide binds to the dye due to salt formation at 1OH. This is the 1OH part of the alizarin. So it is forming a salt with 1OH and coordination at the adjacent carbonyl group. So this is the adjacent carbonyl group. So it forms a coordination bond with the adjacent carbonyl group. This involves the formation of a chelate. Chelate is a complex which has a cyclic structure. So here a cyclic structure is formed. So it involves the formation of a chelate. The chelate structure is responsible for light fastness of the mordant dye. And you can see aluminum is bound to alizarin on one side and it is bound to the protein or the tissue of the fabric on the other side. So it is holding the dye on the fabric. The modern dyes is the most suitable for wool and nylon. The third variety is vat dyes. Vat dyes are a class of dyes that are classified as vat dyes because of the method by which they are applied. Vat dyeing is a process that refers to dyeing that takes place in a bucket or vat. So this is an image of vat dyeing, and here you can see vessels which are made up of wood, and these are called vats. The original vat dye is indigo. This was once obtained only from plants, but now it is produced synthetically also. Now these vat dyes are insoluble in water, but on reduction with sodium hyposulfite Na2H2O3 in a vat form a colorless soluble compound which has great affinity for cotton and other cellulose fibers. The fiber soaked in a solution of a reduced dye is then hung in air or treated with oxidants. The colorless compound is oxidized back to the insoluble dye which is bound to the fabric. So example of vat dye is indigo. Here you can see this is indigo and this is insoluble in water. And this is reduced using sodium hyposulfite and it gets converted into colorless compound, but it is water soluble. And this water soluble compound has affinity for cotton or other cellulose fibers, and this binds to the fiber. Now this is hung in air or it is oxidized, treated with some oxidizing agent, or it is just hung in air. In that process, it is getting converted back into the insoluble dye, now which is bound to the fabric. Now this will get color and the fabric will get the color of the dye. Ingrain dyes, these are azo dyes and these are also called developed dyes. Ingrain textile dyes is also called developed dyes and can be applied directly onto the fabric. Ingrain means the dye is developed inside the fabric. Now many azo dyes do not bond well to the fiber such as cotton. Using the ingrain process, the reactants can diffuse into the pores of the cloth and form dye inside the cloth, the fiber. The larger dye molecules are trapped inside the fiber. Azo dyes are formed by coupling reaction between phenol or naphthol and a diazonium salt. Phenol, this is phenol with OH group, and diazonium salt is benzene with N2 plus and X minus. X can be chlorine, bromine or iodine. If it is chlorine, it is called benzene diazonium chloride. Now the reaction between the two leads to the formation of an azo dye. So we have seen earlier the structure of azo dyes. It contains these N double bond N bonds. So the cloth is first soaked with a solution of the coupling reagent like phenol. So first it is soaked with one of the reagents, phenol or naphthol. Then it is immersed in the solution of an appropriate diazonium salt. And the dye is formed inside the fiber and it gets trapped in the fiber. The azo dye developed in the fiber binds fast to it through the oxochromes. This process is suitable for dyeing cotton and other cellulosic fibers and also nylon. These dyes can be used for making printed fibers. Finally, the disperse dyes. These dyes are used to color less polar synthetic fibers such as nylon, orlon, etc. These dyes are insoluble in water, but they may be dispersed in a colloidal form in water. So, these dyes are in water in the colloidal form. The fabric is then immersed in the colloidal dispersion of the dye, and the fine dye particles are absorbed in the crystal structure of the fabric. Example of a dispersed dye is 1-amino 4-hydroxyanthraquinone.